the University of Michigan during my master's with Keylonnie Miller, Alanson sample, and Nikola Banovic. So assembling structures is a common task in our daily life. Adding interactivity to constructive assembly objects can turn them into tangible user interfaces that can guide assembling tasks or use them to spark creativity in hands-on education. So a way to track constructive tasks is touch-based sensing, such as capacitive sensing and electric connectors. However, they require specially fabricated assemblies. So using those specially fabricated assemblies leads to a high compositionality, which means they can track more complex compositional structures. However, they cannot generalize to arbitrary building blocks. On the other hand, UHF-RFID sensing can track the status of atomic non-metal objects. However, it is not immediately clear how to track composite process with RFIDs. So therefore, in our design space here, RF tracking generalizes better to arbitrary building blocks while having a lower compositionality. So a potential solution is computer vision. However, it's well known that computer vision is sensitive to occlusion and clutters. So now we have identified a gap in balancing generalizability and compositionality in assembly tasks. While computer vision could be a potential solution, we believe there's room to explore lower cost and more robust methods for constructive assembly tracking. So in this work, we present StructureSense, a robust, low-cost, generalizable system for tracking constructive assembly structures based on passive UHF-RFID sensing. Our system uses an off-the-shelf UHF-RFID sensing equipment to gather a movement profile during an assembly task. We feed the movement profile to an MCMC model to infer the structure a user is building, and we built 2 example applications based on our systems, a guidance application and an authoring application. So to further describe how our system works, suppose that the user wants to assemble a lamp with the guidance application we built. So in our guidance application, we prompt the user with step-by-step instructions, as you can see on the top. And for example, here the application is instructing the user to install the shelf highlighted in yellow. When the user completes the installation, our application verifies the built outcome. In this case, the user, as you can see down there, the user follows the instruction correctly. Of course, users can make user errors, so our system prompts the user to fix it by rendering difference between the built and instructed structures. And to account for system errors, we also allow users to correct system detection errors by selecting from a list of all possible structures sampled. So now let's see what StructureSense does behind the scene. Throughout the building process, our system maintains a movement history. Each time when the user moves an object, we increment the time step and associate the moved object with it. For example, here the application is at instruction number 1, and the user is moving the bottom shelf. The system records it and increments the time step to 1. And then the user sets down the bottom shelf and picks up the pole. So the system detects pole number 1 is being moved. And during an installation, as an example here, the system detects the bottom shelf and pole being moved together, increments the time step, and records the movement. The user picks up a second pole, installs it, the third pole, so on and so forth, until the first instruction was completed. So with the movement history, StructureSense infers constructive structures given movement history at each movement step with Markov chain Monte Carlo sampling. We model the prior probability by the number of open connectors left and the balance of the structure. The key assumption here is that a structure is more favorable with more connectors closed and well-balanced. We also model the likelihood based on activeness. The key idea is that the recently moved objects are more likely to participate in a new installation. We measure the activeness and idleness of a structure based on how many time steps the object stays idle. So a movement can imply either installation or a mere inspection, meaning that the user picks up an object, inspects it, and did not actually complete an installation. So for samples of installation, there would be 3 types of structures: the 2 structures that are installed together and the other components that remained idle. For samples with installation, we time the activeness of the first 2 active structures together and the idleness measure of the third remaining structures. For samples of inspection, we simply calculate the idleness of the inspected structures. So also to push the limit of StructureSense, we also explored an authoring system which allows the user to freely create virtual objects with jumbo Lego blocks. After each user movement, our system lists all the possible structures by the sampled probability on the right for the users to select from. So we conducted system evaluation first with synthetic user movement data, and we measured the average sampling time for our system given different MCMC train lengths, the sampling time at each movement step, the entropy of posterior at each different movement step, which measures the certainty of the inference, where a lower entropy means a higher certainty. And we also measure the number of unique structures explored with MCMC at each movement step. We conducted these measurements with both the guidance and authoring applications in the best and worst case. So in the best case, the user confirms what they built and interact with the instruction application. And in the worst case, no user disambiguation was provided. So here's the result for the guidance application. In figure A, we can see there's a trade-off between the train length and the sampling time. A higher train length can better explore the sample space while taking more time. We set the train length to 2000 for the guidance application. And as we can see B, in this configuration, we have average sampling time of 1 second. And in C and D, the entropy in the better case scenario remained low because the user disambiguation constrains the structure sample space at each step. However, with the user disambiguation, without the user disambiguation, the sample structure space becomes larger with the higher entropy, meaning less certainty in the inference. However, in our experience, our guidance application is still to handle this case. However, in the authoring application, we found the limits of our system. So we set the MCMC train length here to 4,000. And without pre-specified final structures, the number of different structures that the user could build at each sampling step grows exponentially. So therefore, our system took longer to sample structures and had a higher entropy. And at last, we conducted a simplified user test with 6 participants. Each participant built the lamp and the duck we showed before. We conducted the same system evaluation with actual user movement data to verify our previous results. We instructed the participants to think aloud and observed how they interact with the system. So during our user test, we observed that the guidance application had satisfactory performance and accuracy. All steps took about 1 second to sample, and only 1 system error occurred and was corrected by the participant. However, the large sample space pushed our system to its limit in the authoring application. Participants experienced a longer response time and often need to search the list of samples for what they built. So to summarize, StructureSense balances generalizability and compositionality by extending the compositionality of RF tracking. However, our system do face challenges in tracking more complex structures with a higher creative freedom. So in the future, we would look for incorporating more fine-grained tracking techniques such as RF localization or UWB. And thanks for listening.
User feedback to. Have you looked at where you could utilize like human feedback as in like the user feedback as a way to disambiguate?
You mean user feedback during the assembly tasks?
Yeah.
Well, actually, this is what our applications did. So for the guidance application, well, there's always a balance between how smart the system is and how much user feedback you would want from them. So initially we actually tried to have the system prompts like little tiny steps, like installation of 1 pole 1 by 1 to the user. However, we find that in a typical construction task, the user would find it to be too distracting. So instead we prompted larger step to the system. Yes.
Okay, thank you. Let's thank the speaker.